So let's look at the function f of x equal to x squared over x squared plus 48. We want to find all the things. If I'm thinking about graphing this one, I really want to find the asymptotes as well. So let's go ahead and go through the process of how we graph a problem like this. So I'm going to find my intercepts. Let's see the y-intercept. If I set x equal to 0, I'm going to get 0. And if I set the function equal to 0, to find the x-intercepts, right, if I set x squared over x squared plus 48 equal to 0, I'm really just setting the top equal to 0, which is going to give me 0. So my only intercept is the origin, okay? Hopefully we can also see that we don't have any vertical asymptotes, because if we set the denominator equal to 0, there's no solution, right? X squared plus a number is never equal to 0. Horizontal asymptote, on the other hand, since the degree on the top and the bottom are the same, the horizontal asymptote is the quotient of those leading coefficients. So our horizontal asymptote is going to be y equal to 1. All right. So now that we've got the basics out of the way, let's find the first derivative things. So, my volume's way low. Okay. So the first derivative, so let's find f prime. So that's going to be, let's see, it's going to be the bottom times the derivative of the top, which is 2x, minus the top times the derivative of the bottom, which is also 2x, all divided by the denominator squared. This is going to simplify pretty nicely. We're going to get, let's see, 2x cubed plus 96x minus 2x cubed, all divided by x squared plus 48 squared. The 2x cubes cancel, so we get 96x over x squared plus 48 squared. My only critical value is 0. Right, because this is never undefined. And if we look at this, we can see that my derivative, if I pick a number larger than 0, like 1, top is positive, bottom is always positive. Pick a number smaller than 0, like -1, top is negative, bottom is still always positive. Negative over positive is negative. So we're decreasing, increasing, which means we have a relative minimum at x equal to 0. And we know that f of 0 also is 0. So we have a relative minimum at the point 0, 0. Also, that reminds me. No, I guess not. Oh, no, someone did mess up. Okay. I will also point out, just because it kind of makes sense to point out here. We also know, so what am I trying to say here? First derivative test for relative extrema, right, says that this is a relative minimum. Doesn't say if it's an absolute or not. However, there is an absolute extreme value test. So this is a first derivative test for absolute extrema, for an absolute max and absolute min, if you have one critical point. So if you have one critical point and the function is defined everywhere on the interval, then if that point's a relative minimum, it's an absolute minimum. And the reason is because, well, look, to the left, the function is always getting smaller. To the right, the function is always getting bigger. There's no choice but for this to be an absolute minimum, because it's smaller than everything to the left of it and everything to the right of it. So if you have one critical point and the function is continuous on the entire interval, right? It doesn't work if you have but if the function is continuous on the entire interval and you just have one critical point, if that point's a minimum, it's an absolute minimum. If that point's a maximum, it's an absolute maximum. We'll also see it in the graph, but it's totally true, right? You can see, oh, well, of course, right? There's only one. It got smaller, then it got bigger. That has to be the smallest thing. Okay. Let's find the second derivative stuff, which is usually a pain in the butt, especially when it's a quotient like this. So here's our first derivative. Our first derivative was 96x over x squared plus 48 squared. Now let's find the second derivative. So again, same process. We're just doing it derivative, and it's going to the bottom. Okay, here's where we have to be a little extra careful. Bottom times the derivative of the top minus the top times the derivative of the bottom is going to be, so I've got some stuff squared. It's going to be 2 times my stuff to the first times the derivative of my stuff, which is 2x. All divided by the denominator squared. That's going to be x squared plus 48 to the fourth. And when you're trying to find critical values, especially for quotients, you really, really, really want to factor as much as possible. I mean, that's generally true when you're trying to find critical values, but quotients especially, you really have to do. So let's see, I can factor out x squared plus 48. What else? So I can also factor out a 96. And I think that's it. And then I'm left with, let's see, from this first part, I'm left with an x squared plus 48. From the second part, I dealt with the 96 and the x squared plus 48 to the first, or I factored them out, but I'm still left with an x times 2 times another 2x, which is a 4x squared. Okay. Oh, I made a mistake. It's not a big one, but it matters. I accidentally forgot the minus sign there, so I should be a minus 4x squared. It is going to matter because it's going to make a difference as far as if I had critical values or not for the second group. And then we're divided by x squared plus 48. I can cancel this one here with one of those there. And so simplifying this, I'm left with, let's see, 96 times 48 minus 4 plus 1 is minus 3x squared, all over x squared plus 48 cubed. I can factor this a tiny bit more. I can factor out a 3. I don't want to do 96 times 3. I'm going to say it's 96 times 3 times 16 minus x squared. And I'm not going to, but we could factor that even one more time as 4 minus x times 4 plus x. But I think at this point, we can totally see that for the second derivative, the critical values are positive and negative 4. So here's my second derivative sign chart. Here's my critical values of 4 and negative 4. And I'm just going to do what I usually do. I'm going to pick something bigger than 4, like 5. And see that the top is 16 minus 25 is negative. The bottom is positive. And then in between 4 and negative 4, like 0, 16 minus 0 is positive. The bottom is positive. And then something more negative than negative 4, like negative 5. Negative 5 squared is positive 25. 16 minus 25 is negative. Bottom still positive. So it's concave down, concave up, concave down. So here's what that means. It means we have an inflection point at both of these, at negative 4 comma f of negative 4 and at 4 comma f of 4. I was lazy and didn't find what f of 4 was. I can go back and find it, right? If we look at our function here, let's see, f of 4 is going to be 16 over 16 plus 48, which is 1/4. Okay. It's also what f of negative 4 is, because this is an even function. So I think we found all the things. Let's graph it. So we have our one intercept at 0, 0. And then we know we have a horizontal asymptote at y equals 1. And then we know, I'm gonna try and scrunch in my x-axis a little bit to make it fit. So let's say here's the point. I know this looks about like 1, but let's say that's 4. I suppose I could lower this, but yeah. So at 4 comma 1/4, I'm getting my inflection point. So here's what we've got. My function is decreasing to there and then increasing afterwards. And it does look like it's concave down, then concave up, then concave down. And then to reiterate what I was saying before, notice that this relative minimum, right? First derivative test, the relative minimum. This relative minimum is also an absolute minimum. It is the absolute smallest y value the graph achieves, or the function achieves. Which makes sense, right? If you think about the function, this function x squared over x squared plus 48, x squared is always greater than or equal to 0. X squared plus 48 is always greater than or equal to 48. So a positive, or I should say a non-negative thing over an always positive thing, the smallest it could possibly be is 0. Okay. Are there questions about anything we did here? I need to get one. I can't find my big water bottle. I don't know where I hid it for myself, so I just use water glasses. For functions like these, would only have that's a good question. The answer is, so I'm guessing what your question is. So the question is, functions like this, sorry, would we only have horizontal and vertical asymptotes? I'm guessing your question is as opposed to slant asymptotes. And the answer that I'm thinking is to your question is, so rational functions like this can have a slant asymptote instead of a horizontal asymptote. This one specifically did not have any vertical asymptotes, but these ones can have vertical asymptotes. But in general, rational functions can have sort of any sort of allowable asymptote. I mean, the only kinds of asymptotes we really concern ourselves with are vertical, horizontal, and slant. So just to kind of quickly address that question, this function, f of x equal to, I don't know, x cubed over x squared minus 9. We're not going to graph this one, but I'm going to tell you two things about it. Thing one, it's got vertical asymptotes at x equal to 3 and x equal to negative 3. Because that's what the denominator is 0 and the numerator isn't. Thing two, there is no horizontal asymptote. And the reason why there isn't a horizontal asymptote is because the degree on top is larger than the degree on the bottom. This is a degree 3 thing over a degree 2 thing. And that's always true. If you have a rational function, if the degree on top is larger than the degree on the bottom, you have no horizontal asymptote. Along with that, if you have exactly the case where the degree is on top is 1 larger than the degree on the bottom. So if the degree on the top is exactly 1 plus the degree on the bottom, right? So in this case, right, the degree on the top is 3, the degree on the bottom is 2, so the degree on the top is 1 plus the degree on the bottom. If that's your case, then we do have a slant asymptote. Also called an oblique. And the way you find the slant asymptote is through polynomial division. So to find the slant asymptote, we do x cubed. Wow, that's not how you write that. Come on. You do x cubed divided by x squared minus 9. And I usually like to fill in the missing powers of x. So I probably write this as x squared plus 0x minus 9. And so what do you multiply by x squared to get x cubed? Oh, it's x. X times x squared is x cubed. X times 0x is 0x squared. X times minus 9 is minus 9x. Subtract. 0, 0. I mean, so you could write these here, right? 0x squared, 0x. And 0x minus 9x is 9x. X squared doesn't go into 9x because its power is higher, so we stop. And we say that y equal to x is our slant asymptote. Yeah. So the degree on top is 1 larger than the degree on the bottom, you will have a slant asymptote. I would say don't stress about this unless your teacher has specifically said, like we've talked about slant asymptotes and I ask you about them. Often they kind of get avoided, but okay, let's look at one or two more things and then, yeah. One or two more things and then optimization. Oh, I should also point out, right? Finding this point here, like if someone said, so finding a maximum or a minimum is optimizing a function, right? If someone said we want to minimize the function f of x, this point here would be the place where it was minimized. So finding the critical values of functions is very much the same sort of process as optimizing a thing. The only, well, one of the differences that typically with an optimization problem, in addition to finding the critical values of your function, you're also having to first kind of set up the function, usually with some constraint, meaning some limiting piece of information. But let me do two more questions about critical values and stuff, and then we'll move on to talking about optimization. So here are the questions people asked. One of them was for the function f of x equal to 2 sine of x plus the square root of 2 over 2 times x squared, to find specifically the inflection points in the interval from 0 to 2 pi. That is all the question asks for. Let's do that one, and then we'll do the other one that someone else asked for. So to find the inflection points, we got to find the second derivative. So here's my first derivative. It's going to be, let's see, 2 times cosine of x plus the square root of 2 over 2 times 2x. The 2's cancel. And then my second derivative is going to be, that's interesting. Yeah, okay. Derivative of 2 cosine x is negative 2 sine of x. And the derivative of the square root of 2 times x is just the square root of 2. And we're going to set that equal to 0. We would, again, I'm kind of skipping a small thing and saying, usually you're trying to find where it's 0 or undefined, but we don't need to look where it's undefined because this is never undefined. So I'm trying to solve this. Let's see, I'm going to have negative 2 sine of x equal to the negative square root of 2, and then divide both sides by negative 2, and you get sine of x equal to the positive square root of 2 over 2. That should be a very familiar value. We know that sine is equal to the square root of 2 over 2 at some angle that's like 45 degrees or pi over 4 radians. Specifically, in the one revolution, right, from 0 to 2 pi, we know that sine is equal to positive root 2 over 2 in the first and second quadrant. So I'm looking for this angle in the first quadrant and this angle in the second quadrant, where the reference angle is pi over 4 radians. So one of the angles is pi over 4, and the other angle is pi minus pi over 4, which is 3 pi over 4. The angles in the third and fourth quadrant would be where sine is equal to negative square root of 2 over 2. So like 5 pi over 4 and 7 pi over 4, sine of those values is negative root 2 over 2. Okay, so these are my critical values. Now here's where we have to be kind of extra careful. I'm going to put these critical values on my number line. Pi over 4, 3 pi over 4. And I'm looking at what the second derivative is doing. So I want to pick something out here, over here, and over here to see if the second derivative is positive or negative. But we can't go too far, meaning I'm actually limited to my domain here. So what I should actually be drawing is kind of a number line that's abbreviated. But really, I'm only allowed to be between 0 and 2 pi. And I should be seeing what this quantity is equal to. If it's, I should say, if it's positive or negative. So let's pick something between 3 pi over 4 and 2 pi. I think pi is super easy to pick. Sine of pi is 0. Negative 2 times 0 plus root 2 is positive. So it's concave up. Okay, something between pi over 4 and 3 pi over 4, I'm going to pick pi over 2. sine of pi over 2 is 1. Negative 2 times 1 plus the square root of 2. Negative 2 is bigger than the square root of 2, so negative 2 is more negative than this is positive, so that's negative. So it's going to be negative, so it's going to be concave down. Now, between 0 and pi over 4 is kind of tough. I don't really think it's a good idea to pick the endpoint, although it's probably safe here. I would just say that I know that between 0 and pi over 4, sine is small, right? I know that sine of 0 is 0. And sine of something just a little bit bigger than 0 is still very, very small. So if I pick an angle that's, slightly positive, so I'm somewhere in this interval, this is going to be very, very small. This is going to be very, very small and negative. If I add root 2, it's going to be positive. So I have inflection points at pi over 4 and 3 pi over 4. I wrote those out of order, though, for some reason. So there's my inflection points for this particular function. Okay, let's look at this other question that's similar but a little bit different. What these two problems indicate to me is that someone's going to be asking you some stuff about trig. So let's look at this next one, and then we'll finally get to some optimization for the last 50-ish minutes, 40-ish minutes. So the other one was for f of x equal to cosine of x plus 1/2 x. Find the critical values, and then evaluate the second derivative, f double prime of x, for each critical value. And I didn't write it down, but I'm pretty sure the question also had the same domain, meaning find the critical values in the interval from 0 to 2 pi. And then evaluate the second derivative. Another way you could phrase this question is find the critical values and then determine if you have a relative max or a relative min using the second derivative test, because that's essentially what we're doing here. So let's find the critical values. So my first derivative is, let's see, derivative of cosine is negative sine. And then derivative of 1/2 x is 1/2. Equal to 0. Okay, so then we're going to have, I don't even need to write this. I'm just going to solve this. So I'm just going to add sine of x over here and say 1/2 equal to sine of x. So sine of x, we know that sine of x equal to root 2 over 2. The angles pi over 4 and 3 pi over 4. We're still going to have answers in the first and second quadrants because we still have sine being positive. And it looks like our angles are going to be, let's see, it's either pi over 6 or pi over 3. I know the sine gets bigger as the angle gets bigger, and this is a number that's smaller than root 2 over 2. So I'm thinking in my unit circle, right, pi over 4 is too big an angle because sine of pi over 4 is the square root of 2 over 2. I need to go smaller, which is going to be not pi over 3, but pi over 6. And then I need the same reference angle in quadrant 2. So the actual angle would be 5 pi over 6. So those are my critical values in this interval. And although we could use the first derivative test, we're not going to. I probably will actually after I do the second derivative test. Let's do the second derivative test. So here's my first derivative. My second derivative, f double prime of x, is super easy. It is, so actually, no, it's not. So my second derivative is going to be negative cosine of x. Okay, this is a case where I probably might even say that the second derivative test is nicer to use. Because check this out. F double prime of pi over 6. Even if you didn't know what cosine of pi over 6 is, we do know that pi over 6 is in quadrant 1 and cosine is positive there. So cosine is going to be positive, which means this thing's going to be negative. So whatever I get here, I know it's going to be negative. It's going to be negative cosine of pi over 6, which is going to be negative root 3 over 2. I suppose I should write that out. Which means that at pi over 6, we have a relative maximum. Because it would be concave down, because the second derivative is negative. On the other hand, the other critical point, 5 pi over 6, well, it's going to have the same value of root 3 over 2, since it's the same reference angle, but 5 pi over 6 is in quadrant 2, and cosine is negative in quadrant 2, right? All students take calculus. So we're going to get negative cosine of 5 pi over 6, which is going to be negative square root of 3 over 2, which is going to be positive, which means it's concave down, which means concave up, which means we have a relative minimum at x equal to 5 pi over 6. And to me, at least for this problem, even though I'm usually a proponent of using the first derivative test, I do think the first derivative test is probably slightly more challenging to execute here. Because if you're going to try to do the first derivative test, and right, we're ending at 0, and then we've got pi over 6, 5 pi over 6, and then we're ending at 2 pi, right? If you want, you have to actually like pick values for each of those intervals. And again, like picking a value here is not super easy. It does end up being, this is very slightly negative, so it ends up being positive. Pick something in between those like pi over 2, sine pi over 2 is 1, negative 1 plus 1 half is negative. And then something over here like pi, sine of pi is 0, plus 1 half is 1. Right, so you still get the same results, that you have a relative maximum of pi over 6 and a relative minimum of 5 pi over 6. But to me, especially when you're trying to determine if an interval is positive or negative for trig functions, it can be a little bit more challenging to do it that way. So second derivative test seems super nice here. Yeah. Okay. Let us look at some of these optimization problems that people were asking about. Okay. Let's see here. Let's do the ones people actually asked about, and then I'll see what I've got. Yeah. Let's look at a couple. Let's look at this one. So this first one was find two numbers that add up to 24 and have a maximum product. Guessing and checking here, although we'll probably will yield the correct result, is usually not good enough for your teachers, right? They don't want you to just guess and check. One, if you guess and check, how do you actually know the thing gave you the maximum, right? Maybe there were some other numbers that you didn't guess that were actually the maximum. So just want to put it out there. Guessing and checking is not the correct path to victory for any kind of optimization problem. You might end up accidentally getting the right answer, or maybe not even accidentally, but like you might get the right answer, but haven't kind of shown that you actually know it's a maximum, but using the process, it's probably not going to be sufficient. All right, so typically with problems like this, we have to start naming things variable names. So two numbers, I don't know what they are, so we're going to give them variable names. Let's call them X and Y is a typical choice. And personally, I've always set up these problems by first writing down the thing that we're trying to optimize. So if I want to maximize product, which we often call capital P, equal to, well, the product is just X times Y. And usually at this point, we stop and think to ourselves, oh, there's something I want to maximize or optimize, but it's got two variables in it, and that's usually a problem. right? 2 variables is too many. So typically, once you see that the thing you're trying to maximize or minimize has more than one variable, you need a constraint. You need a way of relating those two things. So here our constraint, right, our limiting piece of information, is that the numbers have to add to 24. Right? They can't just be anything. If you could pick any numbers, you wouldn't be able to find the maximum because you could be as big as you wanted. But the numbers have to add up to 24. Also something to be aware of, because it's easy to make this mistake. The thing you're trying to optimize should never be equal to a number, because we don't know what its maximum or minimum value is. But I've seen many, many people over the years say, oh, this is equal to 24, right? But the thing you're trying to optimize is just a function. We don't know what it's equal to. But the constraint, that's the thing that's equal to the number that you've somehow been given in your setup, most of the time. So then we're going to isolate one of these variables. In this particular case, it doesn't matter, but usually you want to pick the easier thing to solve for. So we're going to isolate, I don't really care which. Let's say x equals 24 minus y. And then we're going to rewrite our product as x times y. And look, now we have the thing we want to maximize as a function of one variable. So now we can maximize it in the usual way. We're going to find the derivative. P prime of y is going to be 24 minus 2y. We're going to set that equal to 0 / undefined, but again, this is never undefined. And so we're going to get, let's see, y equals to 12. So then two things. Thing one, we have to answer the question. Most of the time the question is find the dimensions that maximize or minimize the whatever of this object, or find the things that maximize or minimize the product in this example. But they're not actually asking for the product. Sometimes they do. But usually they're asking for like what are the inputs and not what the actual product is. So we need to find x, and that's actually going to be the last step, because there's something we technically need to do before this. And now this kind of really depends on the situation. A lot of the time people will ask you to verify that something is actually a maximum, right? At this point, I found a critical value. And I could also find the x value, right? X is going to be 24 minus y, which is also going to be 12. So we found two numbers that add to 24. They're critical values. Do we know they're a maximum? They probably are. But to actually show it's a maximum, you have to do one of two things. Maybe three things, actually. You can either use the second derivative test. Say, okay, well, let's see. My second derivative, p double prime of y, is -2. And so then p double prime at my critical point, where y is 12, well, there's nowhere to plug in the 12, I get -2, which is less than 0, which means the second derivative is negative, which means it's conjugate down, which means I have a maximum. And that is certainly one way to go. The other way to go is to use the first derivative test for having one critical value. So I've got one critical value. It's 12. And then my first derivative is 24 minus 2y. If you pick a number bigger than 12, like 1,000, 24 minus 2 times 1,000 is negative. Pick a number less than 12, like 0, 24 minus 2 times 0 is positive. So my derivative is positive, which means the function is increasing, and the negative decreasing. And look, on the entire interval, right, because this function is literally defined for any value of y, on the entire interval here, before 12, the function was getting bigger. After 12, the function was getting smaller. That means we have an absolute maximum at y equals 12. So usually on an exam, you will need to show that the point you found is actually the thing that it's supposed to be meaning. So they ask you to find a maximum, you actually found something to maximize it. that asks you to find the minimum, you actually found something that minimizes it. So just be careful around that. Let's see. What else have I got here? You guys have some other good questions. Oh yeah, sure. Let's look at, I'm gonna look at two versions of this question because there's an easy version and then there's a harder version that someone asked me via email to go over. So let's see here, what do I got? Find the point closest to 10, 0 on the function, on y, find the point closest to 10, 0 on the curve y equal to the square root of x. You don't have to draw a picture here, but it's nice to draw a picture. So here's my curve, square root of x. And here's my point, 10, 0. And I'm trying to find the point on the curve. I don't know what it is, so I'm just going to call it xy. It's closest to 10, 0. So if you're trying to find the closest point, you're trying to minimize something. You're trying to minimize the distance between 2 points. So what we're actually trying to do here is we're trying to minimize the distance, which is equal to the square root of x minus 10 squared plus y minus 0 squared. Okay, something that's great about this, something you should always do, because it always works. Instead of minimizing the distance, minimize the distance squared. This is something that always will work. If you minimize a thing, right? If you minimize, so I should say, if you minimize something that's positive, right? The distance between two things is always a positive number. Well, if you minimize the square of that thing, right? If you make something square as small as possible, you've also made that something itself as small as possible, if it's positive. So, knowing that the distance has to be positive, we can say, well, if you make its square as small as possible, you've also made the thing itself as small as possible. Great. Which makes the calculations way easier. Okay. So, what's our constraint? It's a little less obvious in this particular question, right? Because there isn't like a number that says like the distance has to be less than something, or the numbers have to add the 24. Right? There's like a, so the constraint, more generally than being just right, the numbers are adding up to something, or right, you have so much fence to work with, or the surface area is less than or equal to this. The constraint is a way of relating your usually 2 variables, right? Again, I've got a thing I want to minimize. It's a function of 2 variables. I want it to be a function of 1 variable. What's a way of relating x and y? Oh, y has to equal the square root of x because this point, oh, the constraint that the point is on the curve, right? It's not somewhere over here, not on the curve. The constraint is that the point has to be on the curve, which means that the y coordinate has to equal the square root of whatever the x coordinate is. So we're going to take this and we're going to rewrite it as our equation now is that the distance squared is x minus 10 squared plus the square root of x squared, which yes, you should just simplify as x. So now let's find the critical values. Notice I didn't simplify this. I wouldn't multiply this out because taking the derivative is probably easier, just as easy if you don't multiply that. So my derivative of my distance squared, yes, you should write distance squared prime, right? You're taking the derivative of distance squared, not the derivative of something else. So the derivative of the distance squared is 2 times x minus 10 to the first times 1. Plus, this is just x, and the derivative of x is just 1. Equal to 0. I'll say a thing in a minute. Sorry. Setting this equal to 0, so I get 2x minus 20 plus 1 equals 0. So 2x minus 19 equals 0, 2x equals 19, x equals 19 over 2, or 9.5 if you have a thing with decimals. Is it a minimum? Good question. So again, you can kind of go, there's actually like a bunch of ways you can say yes, it's a minimum. One way you can say is, well, it can't be a maximum. Why can't it be a maximum? Because I can find, right, this curve goes on and on and on and on forever and ever. I can find points that are further and further and further away. So I can find a point that is further distance from this point, and there's no maximum to that. So it couldn't be a maximum, right? There is no maximal distance to be from this point. It can't be a maximum, so it's got to be a minimum. That is often the argument that textbooks make. Or you could go the second derivative route. You could say, okay, well, d squared double prime, derivative of 2x minus 20 plus 1 is 2, which is positive, which means any critical value from the first derivative has to give you a minimum. Or you could do the first derivative test, which I don't. So I will point out, it is often the case that we kind of default to the second derivative test for optimization problems, because often it's just easier. One of the reasons is because the first derivative test here, if you start looking at the first derivative test, there are some restraints on what x can actually be. Right? So even though this first derivative, right, which is 2x minus 19, looks like there aren't any domain restrictions, the original context of the problem, there are some domain restrictions. Right? X has to be greater than or equal to 0. So if you did try to use the first derivative test, you'd have to start at 0. And then here's your critical value of 19 over 2. And then you say, okay, well, let's, d squared prime. I know it's looking terrible. Pick something larger, you get positives. Pick something, whoops, between 0 and 19 over 2, you get something negative. Like pick 30, this is positive. Pick 1, this is negative. So it's a minimum. And it is an absolute minimum, right? Because everything to the left, it was getting smaller. Everything to the right, it's getting bigger. It's the only critical point, so it's got to be an absolute minimum. So I really want to kind of re-emphasize or restate, there is a first derivative test for absolute extrema. And it only works if you only have one critical value and the function is defined continuous on the entire interval. Okay, the entire interval that we're looking at. Not that it's super important, but the reason you're allowed to use the square of the distance, one is because of what I said before, right? If you make a thing as small as possible, its square is also going to be as small as possible, vice versa. But the other reason is really because of the chain rule, right? If you take the derivative of d squared, well, using the chain rule, the derivative of some stuff squared is 2 times your stuff times the derivative of your stuff. If you set that equal to 0, well, the distance is always positive, so it can't be 0. So you're really just finding where the derivative is 0, which is like finding the critical values. So that's why this always works, is because it's the same math, really. That's a good, so someone asks, can I explain which problems prefer to use the second derivative test and which ones just use the first derivative test for? So here's what I would say. If you're graphing, you should always use the first derivative test to classify your maxima and minima. Because, I mean, all other things equal, if you're graphing the thing, you really want the sign chart for the first derivative because it's going to help you graph the function. Optimization, it really kind of depends on what you like. So it kind of depends on how terrible it is to take the second derivative. And like this problem, no big deal, right? Your first derivative is 2x minus 19. Second derivative is just like, it's right there, right? It's practically for free. So if the second derivative is super easy to take, that is often a good time to do it. So that begs the question, when is it not? Yeah, let's see. So I want to do one more distance question, and then we'll look at a couple of examples where maybe the second derivative is not the way to go. So the unfortunate answer is that it kind of depends. I would say if the second derivative looks easy, go that direction. If the second derivative doesn't look easy, probably use the first derivative test. And there's one other thing I haven't even talked about, okay, which I guess I'll address as well. Yeah, I will have to address that. So let's look at one other problem, because somebody So they asked me this one, and they actually done most of the work right. They just made kind of a small error close to the end. So where'd you go, paper? Yeah, here it is. So same kind of deal. After this question, I might need to take a quick break to grab some water. And maybe. Okay. So the question was, find the point on the line. Oh. I made a small mistake. It's not a huge deal. It's more that I didn't finish answering the question. So the question was to find the point closest to 10, 0. I didn't find the point. I only found the x coordinate. So it's really important with optimization problems that when you get close to the end, like when you found your critical value, maybe you've tested to see if the max or min, maybe you haven't, but that you read the question again and ask yourself, did I answer the question they're actually asking? This question was asking for the point. I didn't find the y coordinate of the point. So I know my x coordinate is 19 over 2. I know it's on the square root, y equals square root of x, so I know the y coordinate is the square root of 19 over 2. So my point to actually answer the question is 19 over 2, comma, the square root of 19 over 2. So do really make a point of looking back to see that you have actually answered the question that's being asked. It is really easy to answer the wrong question and to lose points. Okay, so same kind of question for this one. On the line, 5x plus 4y plus 3 equal to 0, what point is closest to -1, -5? Okay, so same deal. We want to minimize the distance between this point and this line. I don't know what that line looks like exactly. I'm just going to try and I'm going to draw something that might vaguely look like it. I don't really know. There's probably some, yeah, I mean, there's definitely a y-intercept and an x-intercept. Did I draw this even close to being right? Doesn't really matter. -1, -5 is sure like over here. Not really. So I'm looking for the point. Maybe it's right there. Again, my graph might not at all correspond to the data, but I'm just trying to give myself a sense of what's happening. So this point here is the point x comma y. This point here is the point -1, -5. And I'm trying to minimize that distance, or the distance squared. So the distance squared that I'm trying to minimize is x minus -1 plus y minus -5 squared. And then as usual, right, so the thing I'm trying to optimize has too many variables. Has 2 variables. So I need a constraint. The constraint, of course, is that the point is on the line or on the curve that's given. So there's my constraint. 5x plus 4y plus 3 equals 0. Solve the constraint for one of your variables. It does not matter which one usually. In this case, it really doesn't matter. Solving for y plugging in here or solving for x and plugging in here is going to be the same amount of work, essentially. So let's solve for y because it's usually more typical. So I've got 4y equal to -5x minus 3. And then y equal to -5x minus 3 divided by 4. I feel like it might make this a little bit easier if I write this as -1/4 times 5x plus 3. Maybe. Jam that in there. So then my thing I'm trying to optimize is x plus 1 squared plus, it's going to be gross, -1/4 times 5x plus 3 plus 5 squared. While you could simplify the insides of this before taking the derivative, you don't really need to. It's really probably more work than it's worth to do that. And that is usually the case when you've got a distance thing and you're taking the derivative. It's usually often best to not simplify the insides, to not square it out, because the derivative is going to make it so the algebra later is easier if we just don't do the algebra first. So let's take the derivative here. So my derivative of d squared, so some stuff squared is 2 times my stuff to the first power times the derivative of my stuff, which is a 1 and a 1. But then for this, we have to be a little extra careful. So it's going to be plus 2 times my stuff, which is all this, negative 1/4 times 5x plus 3 plus 5 times the derivative of this stuff, which is, let's see, the derivative of negative 1/4 times 5x is going to be negative 1/4 times 5. So negative 5/4. And then the derivative of negative 1/4 times 3 is 0. The derivative of 5 is 0. Okay. I'm going to set that equal to 0. Now, here's the thing that I think I saw people doing that made this problem harder. I'm trying to simplify this fraction here. I would probably start by multiplying both sides by 4 to get rid of this denominator here. So I multiply both sides by 4, I get 0 equal to 2 times 4 is 8 times x plus 1. And then 2 times all this without the 4 over here, negative 1/4 times 5x plus 3 plus 5 times negative 5. That seems a little less terrible. I might multiply by 4 again because there's still a 4 in the number. Let's see what happens. So I get 0 equal to 8x plus 8. Negative 5 times 2 is negative 10. So minus 10 times a negative 1/4 is going to give me a positive 10/4. Ooh, I'm making a mistake there. That is a bad idea. Because that 1/4 isn't applied to each of those things, so I can't factor it out. Let's just say it's a negative 10 like we had. And then I've got inside here a negative 1/4 times a 5x plus 3 plus a 5. Okay. So this is 8x plus 8 minus 10 times minus 1/4 is plus 10/4 times 5x plus 3. And then minus 10 times 5 is minus 50. Still equal to 0. I know this problem is taking forever, but I'm going to erase stuff. Yeah, sorry. So then I probably would multiply both sides by 4. So I would say 0 equals 32x plus 32 plus 10 times 5x plus 3 minus 200. It's just easier not to deal with fractions if you can help it. So then let's figure out what we've got. We've got 0 equal to 32x plus 32 plus 50x plus 30 minus 200. So 82x. Negative 200 plus 30 is negative 170 plus 32 is negative 138. So 82x equals 138. X equals 138 over 82, which reduces to 69 over 41, which I feel like is not what I got. I got something different in my notes here. What mistake did I make here? Let me double check real quick just so I'm not doing something stupid. That looks right. Did I make a mistake in my notes? Let me double check. I just don't want to be telling you guys the wrong thing. Sorry, one moment here. 41. Oh no, I totally. Yeah, I did. Okay, I made a mistake in my notes. Cool. All right, that seems right. So, terrible number, but fine. And then to answer the final question, we have to take this number and plug it back into something I erased. Right? I erased that y was equal to negative 1/4 5x plus 3. So my x value is that, and my y value is negative 1/4 times 5 times 69 41st plus 30. Terrible. I wouldn't simplify that unless I had all the time in the world. Is it a minimum? Yes, because our second derivative, if we look at this, is super easy. Super easy. Right? Our d squared double prime just kind of is 2. And then the derivative of this part here is 2 times negative 1/4 times 5. Which is 2 minus, I don't know. Sorry. Oh. Let's leave that there. Okay, the second derivative is not super easy, but it's still not so terrible. It's certainly positive because it's 2 plus a positive number. So I'm just concave up, so you have a minimum. Yeah. All right. I really need to grab a drink. Also, let me actually give you guys the setup for the problem we're going to work on next. I'm going to grab a drink of water. Maybe also let's see. I should have one right here. Don't care about that. Okay, let's just do this one. Find the dimensions of the largest possible cylinder. Largest meaning largest by volume, whose surface area is, I always forget what numbers make this nice. Fine, we'll just go with janky numbers. Is 100 square centimeters. Okay, so here's the picture of a cylinder. We don't know the radius or the height, right? Those are the dimensions that matter when it comes to a cylinder. So here's what I want you guys to do. I want you to set up an equation for the thing you're trying to maximize. So we're trying to maximize the volume. And then our constraint is going to be the surface area of this cylinder. So that the surface area, which there is an equation for, and I want you to think about it while I'm using the restroom, equal to something, that's going to equal 100. So find the equation for the volume, the equation for the surface area, and if you finish those two things, start isolating one of the variables here. I'll be right back. Okay, so let's see what we've got here. So for a cylinder, the volume is the base area, which is a circle. So pi times the radius squared, that's the area of the circle. And the height is the height. So there's your equation for the volume of a cylinder, pi r squared times the height. Surface area, well, it's the bottom circle plus the top circle plus the around part. Bottom circle is pi r squared, top circle is pi r squared. And the around part, if you remember, is 2 pi r h. Because again, what you can think of is, at least what I like to think of is, this is like a roll of paper towels. If you unwind one paper towel that goes exactly all the way around, well, that paper towel is a rectangle shape with a height of h and a length of the circumference, which is 2 pi r. So the area of the around part is exactly 2 pi r times h. Okay, so then we have to take this equation and solve for one of the variables. And we have a choice. You can either solve for r or solve for h. But since there's only one h and there's an r squared and an r, it's going to be way, way easier to solve for h. So I'm going to say that 2 pi r h is equal to 100 minus 2 pi r squared, and then divide both sides by 2 pi r. So that h is equal to, you can either write it as one fraction, 100 minus 2 pi r squared over 2 pi r. And actually, I probably would write it as one fraction. The reason why I would write it as one fraction is saying I'm going to multiply it back here. When I multiply this by this, one of the r's here will cancel with the r there. So that's going to be good. Okay, so that's our setup. So now we're trying to we have to, I should say, right? We've got our function, our volume that we're trying to maximize, but it's a function of 1, 2 variables. We've found h in terms of r, so we can replace h to write this in terms of one variable. So let's look at it. We've got that the volume is equal to 100 minus 2 pi r squared over 2 pi r times pi r squared. Sorry, I know I said that here. So pi r squared times h, which is that one. Okay. So then I'm going to try and simplify this before I differentiate it. So I can cancel an r here and an r there. I can also cancel a pi here and a pi there. So I can say that the volume is just r times 100 minus 2 pi r squared over 2. Well, I can actually divide each of those things by 2. So that's going to be r times 50 minus pi r squared. And then I might as well distribute the r so I don't have to use the product rule. So the volume is equal to 50r minus pi r cubed. Okay, that's not too terrible. Let's take the derivative. V prime is equal to 50 minus 3 pi r squared. Set that equal to 0. And here's where the numbers are going to get kind of gross. So solving for r, I'm going to get 50 equal to 3 pi r squared. I suppose you could try factoring. The factoring is not typical, but does it's kind of stupid. You shouldn't really factor this. I'm just going to do this, and then I'm going to divide both sides by 3 pi. So 50 over 3 pi equals r squared, and then square root both sides to get r equal to the square root of 50 over 3 pi. Technically plus or minus, but we know the radius should be positive, so just that. So our critical value here is that r is equal to the square root of 50 over 3 pi. Okay, so here's another way to check to see if it's a max or a min. We can use the extreme value theorem, which says that on a closed interval, a function has to have an absolute maximum. A continuous function has to have an absolute maximum and an absolute minimum. Well, here's our function. And although it's kind of a stretch, people do say, well, we can let r be as small as 0. And the biggest the radius could be, oh, that's a good question. What's the biggest the radius could be? Well, the thing is here, we only have 100 square centimeters to work with. So if the height was 0, which seems kind of dumb, but okay. If the height was 0, then this part wouldn't matter. And our constraint would say that, okay, 2 pi r squared equals 100. Okay, okay. Let's a little wait for a second. So solving for r here, you get r squared is 50 over pi. R is the square root of 50 over pi. So because of the constraint, the biggest that the radius could be is the square root of 50 over pi. Any bigger, and you've got more surface area than is actually allowable. And again, I know it's kind of silly because you're basically saying you've got the bottom surface and the top surface, and you've made this 0 volume shape. It's dumb, but it is what people say. So we're limited to a radius of 0 and a radius of the square root of 50 over pi. Okay, so here's what we're going to say. When the radius is 0, what's the volume going to be? 0. And when the radius is the square root of 50 over pi, it might be less easy to see it. When the radius is the square root of 50 over pi, the volume is also going to be 0. Because the height's 0, but also because if you plug that in there, or actually if you plug it in here, maybe easier to see, you get square root of 50 over pi times 50 minus pi times 50 over pi, which is 50 minus 50, which is 0. So here's what we're saying. At this endpoint, the volume is 0. At this endpoint, the volume is 0. And at this critical value in between those two endpoints, the volume is positive, right? If you plug this in here, that's positive, and 50 minus pi times this number is going to be something positive as well. So what we're saying basically is the function does this. It's 0, it's positive, it's 0. And by the extreme value theorem, it says if a function is continuous on a closed interval, it has to achieve its absolute max and absolute min, and they happen at either the critical values or the endpoints. Well, the endpoints can't be the maximum because they're both having a value of 0. And the middle thing has a positive value. Well, that positive value is the only one that can be the maximum, right? It can't be those endpoints there. So that's another way people verify that you have a maximum. So we definitely do have a maximum at r equal to the square root of 50 over 3 pi. I think it's got 3. That's 3 pi down. No, I guess that's right. It just seems, yeah, okay. Yeah. So we're still not done. Right, the question is find the dimensions. So then we have to go back and find h. Okay, there's an equation for each. So here's the nice thing about finding the dimensions. Once you found your one critical value, in this case, r equal to the square root of 50 over 3 pi, I know it's stupid, then we should already have a place where you can find the other dimension. You should have the other dimension in terms of this. So it's not going to be super great, but we're going to go ahead and plug in our r value there. And again, if you're short on time, I would say don't simplify this. So h is going to equal 100 minus 2 pi times the square root of 50 over 3 pi squared divided by 2 pi times the square root of 50 over 3 pi. We could simplify that if we really wanted to. I would leave it alone. I mean, this isn't super terrible to simplify. 50 over 3 pi squared is just, or I should say the square root of something squared is just that. So it does simplify to 100 minus 2 pi times 50 over 3 pi over 2 pi times the square root of 50 over 3 pi. And then the pi's cancel here. You essentially get 100 minus 100 over 3. So you get 100 minus a third of 100. So you get 2/3 of 100 over 2 pi squared, right? It's still gross. You can do more work here and simplify this. And I think it ends up being actually the same as the radius, which is interesting. Or maybe it's twice the radius.